Hey guys, good afternoon. Hope everybody's doing okay. Welcome to the first online lecture. Unfortunately, the iPad recording can't be paused, so I will go as long as I can, but I might need to send lectures in multiple parts. So I'm calling this online lecture number 1, as you can see. I urge you, and I will constantly be giving you problems that will review chapters 6 and 7, which I think are really the core of this semester. And so we'll be using that material throughout the rest of this semester. So obviously the remaining timeline needs to be thought about carefully. So the way I'm going to approach this is I'm going to do chapter 8, so we'll redo chapter 8. I'll start that today. It's been so long since we were in class together that I really feel that needs to be done. We'll do chapter 9, and then, oops, hang on a second. There we go. Let's erase that. So we'll do chapter 8. We'll do chapter 9. And then I think we'll move up to chapter 11, chapter 9, chapter 11, and then we'll come back and do chapter 10. And that might be it. If I can do some nuclear physics near the end, that would be great. But certainly no promises on this end. So let's get into it. I'm going to be again urging you to go back and look at things at the level of university physics. I will send each of you by email a electronic copy of Halliday, Resnick, and Walker if you don't have it at home. And so this is the time to do some review. So anyway, at the end of the day, to put the cart in front of the horse, this chapter is going to really focus on the nature of the electron spin. And for those of you who remember, at least from a general chemistry standpoint, that the electron can come in two spin directions, right? You have the ms quantum number is going to be plus or minus 1/2, and we'll see what that means if you forget. But what I want to do is really let you know how important that is. So for those of you interested in what's going on in physics now, some of you might realize that quantum computing is a looming area, and in regular computing, as you know, all data can be written as a stream, so to speak, a stream of zeros and ones, and again, sort of binary operations, right? And basically, in computing now, 0 would be a voltage off, and 1 would be a voltage on, and so digital information is encoded by a stream of zeros and ones, which actually are voltages on or voltages off. So the interesting thing is that in quantum computing, since the electron spin comes in plus or minus 1/2, then we can have a stream of 1/2s or negative 1/2s, And so the information then is encoded in electron spin as opposed to a voltage. And that's really the foundation of quantum computing. So, this chapter is, in my estimation, an incredibly important chapter, and demands your attention. So let's go back and start to tease this chapter out a little bit. So let's go back and look at the classical dipole moment. And so there's our first detour, right? So you're gonna look this up in Halliday, Resnick, and Walker, which I'll just abbreviate from here on out as HRW. And so do remember that I will be sending you the electronic version of this book, so there's no excuse for you not being able to look up the stuff. So anyway, if we remember, and may not remember completely, but if we look at some charged object of charge Q, mass M, which is moving around in a circular path, that this charge actually moving around actually constitutes a current. So that moving charge actually constitutes a current. And by virtue of that, that current is going to generate a magnetic field. Halliday, Resnick, and Walker. This is fun because I get to have you share some of the burden of going back and looking at this material. By the way, there'll be sort of weekly problem sets that you will get back to me. So we're gonna certainly for the next 5 weeks or so, we're gonna torque it up so you guys end on a really good note. So the magnetic dipole moment, by definition, so this is the symbol for the dipole moment. And again, I talked in class about where this term comes from, but you can, again, look that up if you so desire. So the classical dipole moment is going to be equal to the current times the relevant area that current sweeps around. So this would be the relevant area. We talked in class about the vector nature of the area, and I think that's something you need to go back and review again. And we did do that in university physics. You might need to go back and look up the electric flux, the magnetic flux. And again, that's a Halliday, Resnick, and Walker review. So again, area is a vector, and uniquely described by a vector perpendicular to the patch of area. And again, we discussed that pretty much in class. So the magnitude then, the magnitude of the dipole moment then is going to be the current times the magnitude of the area. And so for this charge moving around in this circular path, and we'll certainly assume a circular path here, even though it's perfectly general, but the mathematics gets a little bit cumbersome. So let's just assume now that we have that we have a circular path of this charged entity, velocity vector, radius vector, and we can think about this in a x, y, z coordinate system. So x, y, and z coordinate system. So if we were to look at the current here, the current then, by definition, is the change in charge over change in time, which we know in the limit of moving the time window ever closer to zero, then this becomes a derivative dq dt. So again, this is a Halliday, Resnick, and Walker lookup if you have some difficulty with understanding the current. So the current then, in this case, which is dq dt, is going to be the charge of whatever the charged entity is going around in the circle over delta t. But delta t is going to be the time it takes to go around one complete cycle. And so then that would be then q sub e over t, where t is the period. T is the period of the motion. This is fun. The stylus doesn't work as well as chalk, but I'm getting used to it. So we can now get rid of time by noting that the velocity, or the magnitude of the velocity, or the speed, is going to be the circumference, which is 2 pi r, divided by the period. And so consequently then the period is going to be 2 pi r over the speed. And then we can actually plug that into here. And we get now that the current is going to be then q over 2 pi r over the speed. And I'll write it this way first. And so the speed is in the denominator of the denominator, and so that comes upstairs. So that's going to be qv over 2 pi r. And so then the dipole moment, magnitude thereof, is going to be equal to the current, right, which then is going to be qv over 2 pi r, times the area, which is going to be then pi r squared. And so then that's going to be q vr over 2 times the mass of the object times the mass of the object. So one of these r's cancel here, the pi's cancel, leaving us with this expression. And I've multiplied by 1 essentially, right? The denominator and the numerator is each the mass of the object. And so then this is going to be then q times, whoops, it keeps on wanting to complete that circle there. So it's going to be q, I'm going to write it this way in a more suggestive fashion, mv r over 2m. Now that's where we need to again go back and to review, and we did this in class, right? So I want you to review probably for the second or third time. By now it should be maybe sticking. Review the angular momentum in Halliday, Resnick, and Walker. recognizing that the angular momentum is equal to r cross p, which in this case is going to be then going to lead to that the magnitude of the angular momentum is going to be equal to rp sine of theta, but r vector is perpendicular to v vector, which means that theta is equal to 90 degrees, which means then the sine of 90 degrees is equal to 1. And so then the magnitude of the angular momentum then is going to be rp times 1, which is going to be then rp, which is going to be equal to rmv. So we see that the circled part of the dipole moment then is nothing more than the magnitude of the angular momentum, and then we can write that the magnitude of the dipole moment is going to be equal to Q over 2m times the magnitude of the angular momentum. So this is really a super important expression. So we'll asterisk that, something that you ought to recognize. You can see my box is not as good as it would be on chalkboard because the level of friction between the stylus and the iPad Pro screen is just a little bit too slick for me. So I will probably not be as neat as I normally am. So let's end here, right? That's going to be the end of part 1. And so I'll move on to part 2 a little bit later today, and got to take care of some other business, and I will get this going again and get it back to you. All right. So hopefully you guys are having a good afternoon.